everyone, thank you so much for joining me for this video. Today's learning objectives are firstly to do with empirical and molecular formula, and then we're going to look at balanced equations and associated calculations. So first we're going to look at how empirical formula is the simplest whole number ratio of atoms of each element in a compound, and how molecular formula is the actual number of atoms of each element in a compound. And we're going to also look at the relationship between these two formulae. And so by the end, we should be able to calculate empirical formula from data giving composition by mass or percentage by mass, and calculate molecular formula from the empirical formula and relative molecular mass. So then moving on to balanced equations and associated calculations, we're going to look at full equations and ionic equations, and also percentage atom economy. We're then going to look at economic and ethical and environmental advantages for society and for industry of developing chemical processes with a high atom economy. And so by the end, we should be able to write balanced equations for reactions studied, and balanced equations for unfamiliar reactions when reactants and products are specified. So also by the end, we should be able to use balanced equations to calculate masses, volumes of gases, percentage yields, percentage atom economies, and concentrations and volumes for reactions in solution. And then at the end, we're going to look at a required practical, which is to make up a volumetric solution and carry out a simple acid-base titration. So now I'm going to start off by introducing the empirical and molecular formulae. So we need to know both of these definitions because you'll be asked to write these two different formulae. So first we have the empirical formula, and this formula is the one which represents the simplest whole number ratio of all the atoms of each element which are present in one molecule of the compound. However, the molecular formula is the formula which gives the actual number of atoms of each element present in one molecule of the compound. And one really important note is that these two formulae could actually work out to be the same. So for example, if we look at methane, which has the formula CH4, this is also the simplest whole number ratio. So its empirical and molecular formulae are actually both the same. However, if we look at something like hexane, so that's C6H14, if we have C6H14 as molecular formula, we can actually find a smaller whole number ratio. And so its empirical formula would not be the same as its molecular formula this time. And so we would have, if we divided everything by 2, we would have C3H7. So that would be our empirical formula for hexane. And so to convert from empirical and molecular formulae, this is the equation we have. So we have that the number of units of the empirical formula is equal to the MR of the compound, so the relative molecular mass, divided by the relative molecular mass of the compound of the empirical formula, so with that empirical formula. And we're going to see how to use this. So now we're going to go on to finding the empirical and molecular formulae. So we need to know how to work out both of these formulae from data giving composition by mass or percentage by mass. So we have a general method, and the first step is to divide the percentage by masses or the composition by masses, depending on what you get in the question, of all the elements by their corresponding relative atomic masses. And this is basically to find how many moles we have of everything. And then we divide all the values by the smallest value, and this is basically giving us the simplest whole number ratio. So then we use this ratio to find the empirical formula. And if we want to find the molecular formula, we then find the number of units of the empirical formula and then multiply every element in the empirical formula by this unit to find the molecular formula. So in this example, a compound contains 40 grams of carbon, 6.7 grams of hydrogen, and 53.5 grams of oxygen. And it has a relative molecular mass of 60. So then we're told to find the empirical and molecular formulae of this compound. So the first thing I like to do is to write out all of the atoms we have, so all of the elements. So we have carbon, and then hydrogen, and then oxygen. And I always find it quite useful to space them out. So the next thing I do is write out everything that I've got. So I've got 40 grams of carbon, and then 6.7 grams of hydrogen, and 53.5 grams of oxygen. And so this is a composition by mass question. And then, so the first step is to divide by the AR of every single element. So that's our first step. So we have 40.0 over the AR of carbon, which is 12.0. And so this gives us 3.33. And then we have 6.7 over the AR of hydrogen, which is 1.0. And so this gives us 6.7. And then we have 53.5 divided by the AR of oxygen, which is 16.0. And that gives us 3.34. And the next step we have is to divide by the smallest. So the smallest we have is 3.33. So we divide everything by 3.33. So we have 3.33 divided by 3.33, and that equals 1. And then we have 6.7 over 3.33, and this is equal to 2.01. And then we have 3.34 over 3.33, and this gives us 1.00. So it's always a good idea not to round these very much, because sometimes if it's 1.5, that is actually what we take it as. So when we try and find the empirical formula, we will use that 1.5 instead of it being 1 or 2. And then the next step is to find the empirical formula. So first what we do is find the ratio. So the ratio we have is 1 to 2 to 1, because this 2.01 is very, very close to 2. And so that's what we take it as. And so we have that the empirical formula is equal to 1 carbon, and then we have 2 hydrogens, and then an oxygen. So this is our empirical formula. And to find the molecular formula, we then find the units, the unit of the empirical formula, and then multiply this empirical formula by the unit. So the molecular formula they've given us, the molecular mass, is 60. So that's the MR of the compound. So we've got the equation that the unit of the empirical formula is equal to the MR of the compound divided by the MR of the empirical formula. So this CH2 that we've just found. And so the unit is equal to MR, which was 60, divided by the MR of this compound with the empirical formula. So we have the AR of carbon, which is 12, and then added with 2 hydrogens, which is 2.0, and then we have 16 for the oxygen. And so this gives us 2, and so therefore the molecular formula is everything in the empirical formula multiplied by 2. So we have C2H4 and then O2. Now we're going to have a look at percentage yield. So what the percentage yield tells us is basically the practical efficiency of a process. So how much is lost by the practical process of obtaining a product, and also by the reactions that don't go to completion. So sometimes we get reversible reactions, or sometimes they're kind of in equilibrium. So we don't get the reaction which fully goes to form all the products. And so the percentage yield can be calculated by doing the mass of product obtained over the theoretical mass of the product multiplied by 100. And we can also do this by dividing the moles of the product obtained and the theoretical moles of product, also multiplied by 100. So in this example, if we started with 3.32 grams of potassium iodide and added 6.62 grams of lead nitrate, find the percentage yield of lead iodide produced. So the first thing to do with all of these kinds of questions is firstly to write out the equation so we know we can see what's happening. So we have potassium iodide, and we're adding this. This should be aqueous, so dissolved in water or solution, and we're adding it with lead nitrate, and this will also be aqueous, and this will go to form our lead iodide, which will now be a solid, and then we also get potassium nitrate, and this will be aqueous. And now we need to balance this equation. And so we see that we need 2 iodines because we have 2 on the right-hand side. So that means we need 2 of these potassium iodides. And that means we'll need 2 of these potassium nitrates because we have 2 potassiums on the left-hand side. And so now all of these should add up. And so the next thing we do is we work out the moles of potassium iodide and the moles of lead nitrate that we have. So firstly, the moles of potassium iodide. So we know that moles is mass divided by the MR. So we have that the mass of potassium iodide is 3.32 grams. And then we divide it by the moles, which can be found by adding up all of the individual relative atomic masses of the elements. So we have 1 potassium, so we have 39.1, and then added with an iodine, which has an AR of 126.9. And so this gives us 0.02 moles. And then we work out the moles of lead nitrate that we have. So we have that the moles of lead nitrate is equal to, again, the mass over the moles. So we have that the mass is 6.62. And then we divide it by the sum of all the ARs. So we have lead, which is 207.2. And then we have 2 nitrogens, so that's 28.0 because 1 nitrogen is 14. And then we have 6 oxygens, and so that would be 96.0. And so this gives us also 0.02 moles. And now we need to look back at the equation to find out the ratio. So we know from the equation, so we have from equation, two moles of potassium iodide, so we know the number of moles because of this coefficient here, react with 1 mole of this lead nitrate. And so first looking at our first scenario that we could have, if we have 0.02 moles of potassium iodide, so we have 0.02 moles of potassium iodide, then this would react with 0.01 moles of lead nitrate because it would react with half the number of moles of this potassium iodide because it's a 2-to-1 ratio. And so we have moles of lead nitrate. And if we looked at a different scenario that we could have is that if we had 0.02 moles of lead nitrate, so starting off with the right-hand side this time, then this would react with 0.04 moles of potassium iodide because this time it's a 1-to-2 ratio. So we have we need double the amount of moles of the lead nitrate of potassium iodide. And so we can see that this one at the bottom can't happen because we don't have enough of this potassium iodide. And so this is the reaction which happens. So we can also say that the lead nitrate will be in excess because we actually have 0.02 moles of this lead nitrate, and we're only reacting 0.01, so we'll have some left after the reaction. And so we say that lead nitrate is in excess. So that is the reagent which is in excess. And so now we can work out the maximum mass, so the theoretical mass of this lead iodide that we could form. Because again, we can use the ratios. So going back to the equation, we have that 2 moles of this potassium iodide will form 1 mole of this potassium iodide because there's a 1 here. And so it's a 2-to-1 ratio. And so we're reacting 0.02 moles of potassium iodide. And this will form 0.01 moles of this lead iodide because it's a 2-to-1 ratio. And so now we can use this to work out our theoretical mass. So we have that the mass of Ki, which is theoretical, so the maximum it could be if we have nothing lost, would be moles multiplied by the MR, because we need to rearrange the equation we have for moles. So we have that the moles is equal to mass over MR. So if we rearranged it to get mass as a subject, we would have mass is equal to moles multiplied by the MR. And so this is what we're using. And so we have that the moles is 0.01. So this is supposed to be potassium iodide. So it's the theoretical mass of potassium iodide that we could obtain from this experiment. And then we multiply it by the MR, 207.2 plus 2 iodines, which is 2 multiplied by 126.9. And so this gives us 4.61 grams. And this is what we call our theoretical mass. So now we can work out our percentage mass. And we do this by using the equation we learned before. So we have the percentage yield, is equal to our obtained mass of lead iodide over our theoretical. So of course this would be the percentage yield of this lead iodide. And so if I told you that the obtained mass of lead iodide was 4 grams, then we would have 4 divided by 4.61 multiplied by 100, because this is what turns it into a percentage. And this gives us 87%. So the yield is actually quite high. Now we're going to go on to atom economy. So the atom economy tells us, in theory, how many atoms must be wasted in a reaction. So the way we work this out is dividing the mass of the desired product by the total mass of the reactants. And so, for example, we're going to look back to our example when we worked out the percentage yield of the reaction between potassium iodide and lead nitrate. So our equation was that 2 moles of potassium iodide reacted with 1 mole of this lead nitrate to form 1 mole of lead iodide and 2 moles of lead nitrate, potassium nitrate. And so the first thing we do is work out all of the masses of the desired product and the reactants. So we have that PbI2, which is the lead iodide. The mass of this is equal to its MR. So we have lead, which has an AR of 207.2, and then we add 2 times the iodine, which is 126.9. So this gives us 461 grams of this lead iodide. And then we have the reactants. So we have 2 moles of this potassium iodide. And so we have to do 2 multiplied by the MR of potassium iodide. So we have 2 times 39.1 plus iodine, which is 126.9. And this gives us 332 grams. And then we have lead nitrate, which is equal to 207.2 plus 2 times nitrogen, which is 2 times 14, plus 6 times the AR of oxygen, which is 16. And this gives us 331.2 grams. And so it's really, really important to remember that we don't work out the mass of the product, which is just the byproduct, because we're looking at atom economy. So actually how many atoms are lost when we want to get to our product, so the one that we actually want. So now we use the equation, and we have the percentage atom economy is equal to the mass of our desired product, which is the lead iodide. So we have 461 divided by the mass of the reactants, so 331.2 added with 332, and then multiplied by 100, and this gives us 70%. So it's actually got quite a high atom economy as well. So now we're going to have a look at some advantages of having a high atom economy. So firstly, we're going to look at some economic advantages. A company using a process that has a high atom economy will make more efficient use of its raw materials. And so less money is wasted if more of the reactants actually produce the desired product instead of producing lots of byproducts. And the company will also have less waste to deal with, and so they can spend less on separating the desired product from the waste products. And another thing to note is that any waste products that are produced need to be disposed of safely, and this can also increase costs further. And if chemical companies can find easier and cheaper ways to mass produce medicines and other useful chemicals, then this means that the chemicals can be sold for lower prices and therefore made more available to a lot more people. And now looking at some environmental advantages, we have that waste chemicals are often harmful to the environment. And because if we have a high atom economy, then we produce less waste. And so we'll be doing less harm to the environment. And it can also be difficult to dispose of waste products in a way that minimizes their harmful effects. Many raw materials are limited, and so it makes sense to use them efficiently so they last as long as possible. And high atom economy processes tend to be more sustainable than low atom economy processes because we use these raw materials for a lot longer before they run out. So now we're going to talk about balancing equations, and we need to know how to balance both full equations and also ionic equations. And we have a few general tips that can help us. So the first is that we have to use the correct formulae, and we can't change them to make the equation balance. And what we mean by that is that, for example, if we look at sodium hydroxide, we have the formula NaOH, and say we need another sodium. We can't change this formula to Na2OH because that's not sodium hydroxide anymore. And so the rule is that we can only change the numbers of atoms by putting a number which we call a coefficient in front of the formula. And this coefficient in front of the symbol tells us how many moles of that substance we are reacting. And it often takes more than one step to balance an equation, but too many steps will suggest that we might have an incorrect formula. And also, when dealing with ionic equations, the total of the charges on each side must be the same as each other. So first we're going to look at full equations. And for this example, we're going to write a balanced equation for the reaction when aluminium burns in oxygen to form solid aluminium oxide. So first we write down all the reactants and products. So we have aluminium, and I'm also going to write the state symbol. So this is a solid. And we're going to react it with oxygen, which is a gas, and I'm going to leave a space just in case we need a coefficient. And then we're going to have aluminium oxide. And to find the formula of aluminium oxide, we need to think about what groups aluminium and oxygen are in, or think about their bonding. So aluminium is in group 3, so it forms 3+ ions, whereas oxygen is in group 6, so it forms O2- ions. So here we have Al3+, and we have oxygen, which is O2-. And how aluminium oxide is bonded is that these ions are bonded together. They have electrostatic attraction. And so to get these to equal each other, the charges, because aluminium oxide is a neutral compound, we need 2 of the aluminium ions and 3 of the oxygen ions. So we have Al2 and then O3, because we need 2 of the aluminium 3+ and 3 of the O2-, and this will be a solid. So now we actually look at how to balance this. So first I start off with aluminium. So we have 1 on the left and 2 on the right, and that means we need 2 on the left. And then for the oxygen, we have 2 on the left and 3 on the right, and so that means we need 3/2 on the left. And we can also use whole numbers if we want to. So if we multiply everything by 2, we would get 4 aluminium atoms, and then we would have 3 of the oxygen and then 2 of the aluminium oxide. So that would still work. And now we're going to look at ionic equations. So the first one we're going to look at are some neutralization reactions. So for example, write a balanced ionic equation for the reaction between sulfuric acid and sodium hydroxide. So in these neutralization reactions, we have an acid reacting with an alkaline to form a salt and a water. So what we have is sulfuric acid, which is H2SO4, and it's going to be aqueous. And we're going to react it with some sodium hydroxide. And this is going to form the salt sodium sulfate. And because sodium is in group 1, we need 2 of these because our sulfate ion is a 2-. And this is a salt. And then we also have water forming. And the next step to do is to balance this equation. So firstly, looking at the sodiums, we have 2 on the right, and so we must have to have 2 on the left. So we need 2 of these sodium hydroxides. And then we look at everything else. So for oxygens, we've got 6 oxygens on the left, and we have 4 on the right, and so we must have to have 2 of these waters. And now we look at the sulfur. We've only got 1 sulfur on each side, so that's fine. And then quickly checking the hydrogens, we have 4 on the left and then 4 on the right, and so this is our balanced equation. And so the step we do now is to look at all the ions which are present in all of these reactants and products. So the sulfuric acid is made up of 2 of these H+ ions and a sulfate ion. And the sodium hydroxide, we have 2 of these Na+ ions and also 2 OH- ions because we've got 2 moles of sodium hydroxide. And then here we have 2 moles of Na+ ions and 1 mole of sulfate ions. And then we have 2 waters. And we can see that on the left-hand side of this equation, we have a sulfate here and 2 Na+ ions here. And we also have 2 Na+ ions here and sulfate ions here. So these actually don't change, and they don't affect the reaction which is happening, which is the neutralization reaction. And so we call these spectator ions. So if I put a star and label it here, these are spectator ions. And so the ionic equation for this reaction would actually just be 2 H+ reacting with 2 OH- to form 2 waters. Or you could divide everything by 2, and so you'd have 1 H+ added with 1 OH- to form a water. And so for the second reaction we're going to look at, we have a quite similar thing. So we have a precipitation reaction this time, and this is between barium chloride and sodium sulfate. So a precipitation reaction is basically just one where we're forming a solid from 2 aqueous substances. So we have barium chloride, which has the formula BaCl2, and this will be aqueous. And we're going to react it with sodium sulfate, which is Na2SO4, which is also aqueous in this experiment. And then we're going to form barium sulfate, which is our precipitates, our solid. And then we also have sodium chloride, which is going to be aqueous. And so again, we balance it first. So we have 2 chlorines on the left, and so we have to have 2 on the right. And then now this should be balanced. And again, we then write out all the ions we have. So here we have a Ba2+, so a barium 2+ ion, and then I have 2 of these chloride ions, 2 of these sodium plus ions and then 1 sulfate ion. And now what we do is leave this barium sulfate alone. So we don't look at the ions inside this barium sulfate, because the whole point of the precipitation reaction is to form this solid, this precipitate. And so now we go on to this sodium chloride. So we have 2 Na plus ions and also 2 Cl minus ions. So now we have our spectator ions, the Na pluses and also the Cl minuses. And so the ionic equation for barium chloride and sodium sulfate reacting is actually just Ba2 plus ions reacting with an SO4 minus ion to form barium sulfate. And of course, these two will be aqueous, and this will be a solid. And for the first example, the H plus and the OH minus are both aqueous, and then the water is a liquid. So now looking at the third example, we're going to look at some reactions with carbonates. So we're going to look at sodium carbonate and hydrochloric acid. So when we add a carbonate with an acid, we form carbon dioxide, a salt, and also water. So sodium carbonate has the formula Na2CO3 because the carbonate ion has a 2- charge. And then we add, so this will be aqueous. And then we add some hydrochloric acid, which is HCl. This is also aqueous. And then we form the salt, which will be sodium chloride. So we'll have NaCl. This is going to be a solid. And then we're going to have carbon dioxide, which is a gas, and also water, which is a liquid. And now we balance the equation again. So we have 2 sodiums on the left, and so we must have 2 sodium chlorides on the right. And then looking at the hydrogens, we have 2 on the right, and so we must have to have 2 on the left. And so we have 2 chlorines on each side, so that's fine. And then we have the right number of oxygens. So this is our balanced equation. And so now again, we look at our ions. So here we have 2 Na plus ions, and then a carbonate ion, so a CO3 minus. And then here we have 2 H pluses and 2 Cl minuses. Here we have 2 Na pluses and 2 Cl minuses. And then we form our carbon dioxide and water. So again, we spot our spectator ions, which are these Na pluses and also the Cl minuses. So our ionic equation is CO3 minus, which is aqueous, added with 2 moles of H plus, so basically the acid, and this will form our carbon dioxide gas and water. And now finally looking at our last reaction, which is the reaction of ammonia with an acid. So when we react ammonia with an acid, we form an ammonium salt. So write a balanced equation, an ionic equation for the reaction between ammonia and sulfuric acid. So we do exactly the same thing. We have ammonia, and this is going to be aqueous. And then we have our sulfuric acid, which is H2SO4, and this is also aqueous. And we're going to form a salt, and this salt is going to be NH4, 2, and then SO4. And this is going to be solid. And so again, we balance the equation. And so we have 2 nitrogens on the right, and so we have to have 2 on the left. So now we look at the ions again. So we're using ammonia, and so this is actually just going to be ammonia. We don't have any ions here. And then for sulfuric acid, we have 2 H pluses, and then an SO4 minus. And then here we have 2 NH4 pluses, and also a sulfate. And so our spectator ions are just these sulfate ions. And so our ionic equation is 2 ammonias added with 2 H pluses goes to form 2 NH4 pluses. So basically when we add ammonia to an acid, we can form this ion of NH4+. And now we're going to look at moles of gas. So gases are usually really light, so basically they have a very low density. And this makes it very difficult to weigh them in the same way as we weigh solids, so with a balance. And so when we want to know how many moles of the gas are present, we can use the volume instead of the mass. And the general rule that we have is that 1 mole of any gas at room temperature and pressure occupies 24 decimeters cubed. And we saw how we could get this from the ideal gas equation. So if you look back to the ideal gas equation video, then you'll be able to see how we found this 24 decimeters cubed. And so we can form this equation: moles of gas is equal to the volume of the gas in decimeters cubed divided by 24 decimeters cubed. And actually, if you wanted to work it out in centimeters cubed, that would be fine also, because it's just a ratio. But you have to make sure that both the units of the top and bottom of this fraction are the same. And to remind you of the conversions, we have that 24 decimeters cubed is equal to 24,000 centimeters cubed, and it's 0.024 meters cubed. Because we have to divide by 1,000 to get to meters cubed. And one really useful one to know is actually that 24 decimeters cubed is also equal to 24 litres. So we have that 1 decimeters cubed is equal to 1 litre. And so, for example, we're going to work out the volume that 8 grams of oxygen gas will occupy at room temperature and pressure. So the general rule that we have here, we have to remember that this is at room temperature and pressure. And so those are the only conditions where 1 mole of any gas will occupy 24 decimeters cubed. So what we need to do here is to work out how many moles of this oxygen gas we have. And so then we can work out what the volume is. So we have that the moles of oxygen is equal to the mass over the molar mass. So we have 8 over the molar mass of oxygen, which is 2 times 16.0. And so this gives us 0.25 moles. And so we must have a quarter of this 24 decimeters cubed, because we only have 0.25 moles. We don't have 1 mole. And so to find the volume of the gas in decimeters cubed, we rearrange this equation that we have with the moles of gas and the 24 decimeters cubed. So it would be 0.25 times by 24, and this equals 6 decimeters cubed. So now we're going to have a look at titration calculations. And titrations can be used to find the concentration of a solution. So for example, an alkali, by reacting the acid with an alkali using a suitable indicator. And so the two things that we need to know is the concentration of the acid being used, and also the equation for the reaction between the acid and the alkali. So a bit later on, we're going to be looking at the required practical, which is a titration. So that's when I'll go through what a titration actually is. But we're just going to look at how to calculate the concentration of a solution, so the unknown concentration, from the concentration of the other solution. So in this case, it's going to be an acid, and using the equation. So our example is, what is the concentration of sodium hydroxide if 25 centimeters cubed of the solution is placed in the conical flask and 18 centimeters cubed of 0.35 moles per decimeters cubed was needed to neutralize the sodium hydroxide? So the first thing we can do is write out the equation. So we have some sodium hydroxide, and this is in solution, so we call it aqueous. And then we have some hydrochloric acid, and this is also dissolved in water. And this will form a salt and a water because this is a neutralization reaction. So we have the salt, which is sodium chloride, and then we also form water. And this equation is already balanced, so we don't need to add any numbers. So the next thing we can do is work out the moles we have of hydrochloric acid. And so we have that the moles of HCl is equal to the concentration multiplied by the volume. So we have the concentration is 0.35 and then multiplied by the volume, but the volume has to be in decimeters cubed. And so we have to convert this 18 centimeters cubed, and we do that by dividing it by 1,000 or multiplying by 10 to the power of minus 3. And so we get 6.30 times 10 to the minus 3 moles. And now what we can do is use this equation to find the ratio between sodium hydroxide and hydrochloric acid. So from equation, we have that 1 mole of hydrochloric acid will react with 1 mole of sodium hydroxide. And so if we have 6.30 times 10 to the minus 3 moles of hydrochloric acid, then this must react with 6.30 times 10 to the minus 3 moles of sodium hydroxide because they're in a 1-to-1 ratio. And so now we can work out the concentration of our sodium hydroxide because now we have the moles of it and also the volume. So we have that the concentration of this sodium hydroxide is equal to, so we need to rearrange the formula we have. So we have moles is equal to concentration multiplied by volume. And so the concentration must be equal to moles over the volume. And so we have that the concentration of sodium hydroxide is equal to 6.30 times 10 to the minus 3 divided by the volume, which is our 25 centimeters cubed. And so we have to convert this to decimeters cubed again. So we have 25.00 times 10 to the minus 3 because we have to divide it by 1,000. And so this gives us 0.25 moles per decimeters cubed.